Okay, welcome everybody to the fifth in our series of causality seminars organized by the Institute of Data Science and Artificial Intelligence at the University of Exeter. One of the great things about this institute is that it is cross-cutting. So we've already heard from people from the business school. We've heard from people in social sciences, from School of Medicine. And now it's with great pleasure that I'm introducing Professor Eleanor Murray from the School of Public Health at Boston University. There are a few people who, whatever they produce, I read, and whether that's a paper or a tweetorial, but if there's a few people like that, and Ellie is one of them, whatever she produces is worth reading just to get an insight into cutting edge methods in epidemiology. So it's always fascinating. She's a real inspiration, and she's not afraid to get stuck in to real current thorny issues and apply her considerable expertise to those. And it's really inspirational. She's a true academic with a social conscience, and I think it's something that we should all be aspiring to do a little bit more of, because it's very easy to just write our papers and not actually engage. And I know that her tutorials have formed the basis of many of my lectures, and for that alone, I am incredibly grateful. So I'm going to just hand over to Ellie now. The ground rules are, we've got some people who don't want to be recorded, so I will stop the recording at the end when Ellie finishes speaking, and then we can have some questions. But otherwise, I'm going to hand over to Ellie.
Great, thank you so much. Just share my slides here.
Oh, one other thing, sorry, Ellie. If you can leave on your video just to give some feedback, it's quite nice. There's no pressure. There's lots of reasons why people might not want to have their video on, but if you did, it would be greatly appreciated. Thank you.
Yes, if you do want to turn on your video, that way I can tell if things are too basic, too intense, or just boring, and speed up or slow down as necessary. So thank you, Mark. I'm really happy to be here today. It's unfortunate that I can't be there in person, but hopefully one day I'll make my way over there. So today I'm going to talk about causal inference for complex and time-varying exposures. The subtitle of this is "Why the G formula is the only formula you'll need." You may notice in the background I have a embroidery that says "The only formula is the G formula." So this is my general approach to everything. If you can reframe it in a way that links it up to the G formula, then you're good. So that's how I kind of approach a lot of this stuff. All right. So starting just from the very, very basics, what do we want to know? So when we're talking about causal inference, what we would ideally like to know is, what will the world look like in the future, and how might that be different if things had changed in some way? And so ideally we would have a time machine, and we could compare the future under different realities of actions we take, and then pick the best one. Unless the BBC is hiding it, we don't have a time machine. But instead, we want to frame our questions around what is the causal effect of making some decision, of not making a decision, delaying a decision, and always thinking about what are those alternatives that we can think about. So that obviously raises the question, how do we estimate causal effects? So I always like to start with Miguel Hernan's two-step algorithm, which is a simple, easy way to estimate causal effects. First, ask a good question. Second, answer that question. Which is really great, easy to remember, but a little bit easier said than done. So this is kind of the piece of things I'm going to talk about. How do we ask good questions? How do we answer those questions? Okay, so if we can't have a time machine, which we don't have yet, then the next best thing that we would like to have to estimate causal effects is some kind of ideal, perfect randomized trial. The tightly controlled lab experiment on humans that would give us a nice contrast of causal counterfactual outcome estimates. And so I think it's useful to think about what are the features of that ideal perfect randomized trial so that we can keep that in mind as we think about other types of studies and actual studies we conduct in the world. So first, in that ideal perfect trial, we want to make sure that the population we recruit and study is actually the population we want to make a decision about. If we can't get the exact population we want to talk about, then we want to make sure that we're recruiting a population where we expect the causal effect to be the same as in the population we want to talk about. And so there's assumptions around effect heterogeneity, effect modification, that kind of thing. We want to make sure that in our perfect ideal randomized trial, the interventions that we're imposing on participants are exactly the interventions that we're going to be choosing between when we're making a decision. And this, kind of lines up to turn this out to be kind of one of the hardest pieces in a lot of what we do in causal inference. In our perfect trial, everybody would do exactly what we assign them to do for the full duration of the trial. Our randomization mechanism would work perfectly and our sample size would be large enough that we wouldn't have to worry about any kind of small sample bias. No one would be lost to follow-up, and no one would experience a competing event that we hadn't considered and accounted for in our definition of what we want to know about. Our outcome variable would be measured perfectly and without error in all individuals. And kind of linking back to this idea that our population is what we want to know about, the causal effect would either be homogeneous in everyone in our population, or if the causal effect differs in different groups because of effect modification, that we would know about that mechanism and we would have measured those variables that identify which different groups have different effects perfectly and without error, or we would be for sure clear that we didn't care about it. So for example, we may have heterogeneity of effects, but we know that all effects are in the same direction, and then we might not care if some people the effect is slightly smaller than others. But we wouldn't want a situation where the effect was harmful in some people and beneficial in others, and we hadn't accounted for that stratification variable. So this is what ideally we would like to do. And it's basically unattainable perfection, but so even when we try to do a trial, we can't do a perfect trial. But often we can't do a trial at all because we can't intervene. And so that might be that we're interested in a harmful exposure. We might have time constraints, although we've done some very rapid COVID trials. So that one is sort of asterisk these days. There may be cost constraints. It may be hard to access the population we're interested in. We see even with COVID that pregnant people and children are the last to get trials done about them because these special populations have a lot of special protections. And so, we would like to do that perfect trial. Sometimes we can do a trial. That trial is still not going to be perfect. And so we still need to think about how do we recover what we would have learned from the perfect trial. But lots of times we can't do trials. And so that's kind of the basis for why we need to talk more about causal inference. If we had those perfect trials, it would just be a matter of calculating the answer from the trial. So if we can't have this ideal perfect trial, we would like to emulate what would have happened if we had done one. And this is the basis for all of the way that I'm going to talk about causal inference. How do we figure out what would have happened in that perfect trial if we could have run it, given that we can't run it? And this is tricky because everything that goes wrong in your real trial, everything that happens in the real world to make observational data occur in the way it happens, all complicates using actual data to figure out what would have happened in that perfect trial. Some of the particularly tricky questions are who should be included in observational data, especially when does baseline start, and why exposure happens or not. So the way to address this is to be really explicit about what is that perfect trial that you want to do if you could do it, and then how do you move from that trial to actual data analyses, and what assumptions accompany that? What potential biases accompany that? because we're never going to be perfect, but we can at least be explicit. And if we're explicit, then the next person or the next time we do something, we can build on those assumptions that didn't quite fit or those sources of bias that we couldn't quite get rid of. So I want to talk a little briefly about the target trial framework and what I mean by that. So I have a kind of 5-step process, but step 0 is ask a good question. So decide what causal effect or causal question you're asking about. And this really should happen before you figure out what is the trial you're going to do to answer this question. Then step 1 is specify what that perfect ideal trial that you would like to do is. Step 2 would be then determining what is actually feasible to do in the real world. And that might be a randomized trial. It might be something like a pragmatic trial, might be a cohort study or a case control study or a simulation model, depending on what kinds of amounts of information and time and resources you have. But then based on that feasible study design, you want to go back through your perfect ideal trial layout and say, okay, how do I match as closely as possible what I would have done in the trial with the study design that I have, with the resources I have? And then finally, you can do your analyses. So in terms of asking a clear question, I think this is often a really tricky piece, because a lot of the things we want to know about are not things that we can actually ask clear questions about. And we have to kind of own up to that and think about what else we can do or what other types of questions we can ask. So some ways of thinking about what makes a good, clear causal question, thinking about exactly what exposures you're interested in, exactly what comparison groups, exactly what outcomes, thinking about what intervention you would like to do if you could do an experiment, what time points you would do them at, how that would help you make a decision. And I often find, especially when I'm working with clinicians, the most useful thing is to say, okay, if this is to inform a clinical decision, what patients would you be thinking about when you're trying to decide, should you give this treatment or this other treatment? Should you treat now or should you treat later? Who are those patients that are coming in where you don't already know what your decision is and you want to make a decision? What stage of their disease are they at? What information do you have about them? And all of those pieces kind of go into framing what is the question we want to ask, because that's the decision that we want to inform. And so, outside of healthcare, we can think of the same thing. What is the decision that you're trying to make? Who's trying to make it? And when are they trying to make it? And this is important because a lot of what we do is not just yes or no questions. Should I do this one thing or this other thing at one time point, and then it'll be done. We're often asking about complex exposures that have multiple parts or occur over time or have a lot of variation in how they can happen. And complex exposures like this can give us complex answers, even if we can do a perfect trial. So for example, there was this trial a couple of years ago that looked at a assigned diet and exercise regime combination with an outcome of weight loss. And that trial found a sort of small benefit, but all of the news pieces that discussed this trial focused specifically on the assigned diet component, which was some particular brand of smoothie. And they were all like, miracle smoothie helps people lose weight. But the trial arms were smoothie plus exercise or no smoothie plus no exercise. And so, this is an example where that's a complex exposure, smoothie and exercise, that we can't just unpack because we like the idea of promoting the smoothie or we like the idea of promoting the exercise. So even when we do an intervention, when we have a complex intervention, we might need to think, we might not be able to unpack, what pieces do we need? How does the timing matter? How does it, as well as how does it work in other types of groups, even if our trial is as close as possible to a perfect trial. So it's useful to kind of stop and think about what makes an exposure complex. And so, these are the sort of categories I have thought about The first is that you have multiple components. So this would be an example like the exercise and diet trial, where if you have multiple components, it can be hard to define what the different exposure categories are, and it can be hard to measure them. Other things that fall into this could be things like socioeconomic position, treatments like cognitive behavioral therapy. If you have interference between individuals, so if infection can transmit, but also if individuals can share information about the exposure, can share behaviors or habits, that can make it really complex, because now I need to worry not just what my exposure is, but what the exposure of all the people that I'm in contact with are, and potentially what the exposures of all the people they're in contact with are. And I think this is something where we've all kind of encountered a strong reminder of the importance and the challenge of this with COVID. Then exposures that vary with space can also be complex. So, thinking about something like air pollution or something like access to goods and services, if where you are matters for what types of exposures you can access, that makes it complicated or complex. Exposures that vary over time are similarly complex. And this one is, I put it kind of lower in the list to work people up to it, because I think this is one that we don't necessarily think of enough as complex, but most of the medications that we use, most of the habits, most of the diet type questions, we're interested in biomarker questions. All of these things are exposures that can happen, can and do happen over people's entire life potentially, but over many time points, and that makes them complex exposures. And then lastly, a simple exposure that can happen at any time is also complex, because the timing of when that happens is potentially going to depend on the fact that it hasn't happened yet at previous time points. So something like a surgery, where you might think, surgery or no surgery seems fairly straightforward. If that surgery can happen at any time, it suddenly becomes complex. And so based on all of this, I have, after many conversations with people, not really successfully identified any exposure that is not complex, at least in the public health sphere. So if anyone has ideas, I love to hear them afterwards. So we're dealing with exposures that are complex and relationships that are complicated. And in epidemiology, we see this particularly. And one of the pieces we have to deal with a lot is this fact that treatments and other exposures happen over time. And as they happen over time, they tend to also affect the future values of variables that affect themselves future values of that exposure. And so we have this seeming loop. And a lot of times you'll hear people say that these feedback loops mean that we can't do anything. And it's true that these feedback loops do exist, but it's important to remember that they're not actual loops. So, time flies like an arrow, fruit flies like a banana. Instead, we have to cut the loop and think about each time point, so that each treatment or exposure time point is caused partly by some prior experience and causes some later experience, and on and on. And these things, nothing in the future is causing anything in the past. So it's not really a loop. It is all still flowing, obeying the laws of physics as we have established them. But where this gets tricky is when there's not a clear starting point. So an example of a project that I worked on, where we were looking at post-traumatic stress and suicide. And if you have individuals where you start them, at the time they experience trauma, then it's maybe clear to say, okay, that's the beginning of the loop. There's this post-traumatic stress, treatment, substance use, et cetera, loop that happens that potentially culminates in suicide attempt. But what if you're interested in looking at individuals who are some point further on in their experience, perhaps people who have had PTSD for quite some time, have not been very successful in responding to treatments? In that case, is PTSD a starting point or is treatment a starting point? And where do you cut that loop to say, okay, this is baseline, and that's where we're going to follow people on from? And the choice of that is really important for figuring out, how you're going to model this and which population you're going to recruit, what question you're going to ask, what variables you're going to include. And so this can be one particular problem with thinking about these feedback loops. And so that's the sort of conceptual, why is it hard? The technical, why is it important to have a good question aspect is that when we're thinking about asking a causal question, we're really, kind of referring back to that idea of what is the intervention that we can do to set people's exposure level so that we can then say, this intervention combined with the exposure level we set it at is a cause of this much change in the outcome compared to this other one. But for a lot of our exposures that we're interested in, we don't really have a good sense of what are all the ways to set that exposure. And this is particularly true for things like biomarkers. So we can imagine, that this little dude here has high blood pressure, and we have a population of individuals with high blood pressure, and we want to know, is the high blood pressure a cause of heart disease? Important question everyone might want to know the answer to, not one we can really specify because we don't know how this little dude's high blood pressure came about. We don't know if it's because of diet or genetics or exercise behaviors or medications that they're taking or other lifestyle factors. We don't know how this little guy's high blood pressure came about. We don't know how, for our study population, all of their high blood pressure status or not high blood pressure came about. And we don't even know all the possible ways in which it could have come about. And so if we are just looking at high versus low blood pressure and trying to estimate a causal effect on that, the best we can really do is say this causal effect of high versus low blood pressure on heart disease is a weighted average of all the ways in which people in our population came to have high versus low blood pressure, where we don't know what those ways are and we don't know what the weights are. So this is something that we've called the weighted average causal effect, or WACE. And sometimes we want to know this. If we have a very clear population that we for sure want to talk about, and we know that that population really represents the population we want to make decisions about, it could potentially be useful to know. But if our population is just sort of a group of people we happen to get, and we don't have any reason to think that the ways that their high blood pressure came about and the frequency with which those occur are the same as the population we want to talk about, then the WACE is really not useful because it's very unlikely to be transferable to another population. And even if it is transferable, we don't know how or to which populations. So that's the first technical reason why it's important to have a clearly defined causal question. But the second reason is if the intervention or the way the exposure comes about is ill-defined, then it's almost certain that the confounding is also ill-defined, because all of those ways in which our little dude got high blood pressure all themselves also have causes. And if we don't know what all those ways are, then we don't know which of them are confounders, and we don't know which of the causes of those are confounders. And so chances are, even if we're happy to estimate the WACE, we can't estimate it without bias. So we can avoid this whole problem just by focusing on really clear, well-specified causal questions. So briefly, what does that look like? So for example, we might want to know whether gender is a cause of poverty among people who worked for tipped wages. And I guess, I'm not sure, in the UK, you maybe don't have this ridiculous setup, but in the US, there is a separate minimum wage for people who work for tips. And that minimum wage is like something around like $2 an hour compared to, 7 or 8 or 10 for other groups. And the idea is that those tips are part of the wage that's expected to get them up to the actual minimum wage. So this question is relevant in the US, and maybe it's not so relevant in the UK if you don't have a separate tipped minimum wage. So if we wanted to answer this question and we said, okay, we're just going to ask it as is, what does that mean in terms of the interventions that we'd be specifying if we compare, you know, men and women and their poverty outcome in tipped workers? Well, the causal question that would translate to is, what is the difference in total income, or what is the difference in probability of being in poverty for all tipped workers if all of those tipped workers had been women versus if those same tipped workers had been men? So not if our tipped workers had been men from a separate pool, but if those same individuals had a different gender. And that is not the question we actually want to answer, first of all. But second of all, it's not a useful question, even if we thought we might want to answer it. It's not useful. We're not going to do anything about that. And so instead, we want to think about how do we frame this in a way that we can do something to address the reason why we're asking this question. So, and this is maybe a little bit small in the bubble there, but you can see how it gets more complicated when you try to get more specific. But we might instead ask a question. If women who worked for tipped wages received the same amount of tips as their male colleagues, would their poverty risk decrease? And now we're thinking about a comparison of counterfactuals between if all women who worked for tipped wages received the amount of tips they typically received versus if that same group of women received a different amount of tips, that is the amount of tips that their male colleagues receive. And that's something where, you know, we could feasibly do that in a trial, right? We could enroll some tipped wage workers and just tally up how much the men in the study make at the end of each shift, and then tally up how much the women make and make sure, you know, in one arm that we then paid the women extra to compensate or took away some money, I guess, if the women are making more tips than their male colleagues. And it's also something that can lead us to an action for potential policy interventions, right? If it's clear that if women got the same amount of tips as their male colleagues, they would be less likely to be in poverty, then this tells us that we do need to do some kind of targeted you know, economic intervention, economic policy for women. And so this lets us actually move forward to doing something about the reason that we're asking the question. Okay, so this table here, and I'm not going to go through it, but just kind of gives an outline of once we've figured out our question, we move to step one, specify the target trial protocol. This is just kind of an example of the sort of thing we might include in there. And sorry, the reference got cut off the bottom of the screen here, but I'm happy to send a link to this later. But basically, we want to specify, you know, all those components of the trial that we would think about if we were doing a perfect trial. And one of the things we kind of learned from this is that we would like to do that even if we're going to do an actual randomized control trial, because in randomized control trials, we still have real potential sources of bias, informative censoring, non-random non-adherence, competing events, which are not exactly biased, but do change our causal question and so need to be taken into account. We can still have poorly defined causal questions where we have, you know, comparison groups that are unclear or multiple complex interventions. We can have generalizability and transportability problems, and we can incorrectly interpret our results because we don't know what we're doing about all of these different things. So, you know, maybe we've used a complete case and ignored competing events, and then we're interpreting it as just the general overall effect of our drug, but actually it's only if the censoring is completely random and only in people who don't die. That would be important to know. And then, so, you know, the target trial can help us with that because we can think about what we would have in a perfect trial and what we expect in our actual trial. And then similarly in observational studies, we have all those biases plus baseline confounding, less likely in an actual randomized trial, more likely in an observational study. time zero or mortal time bias is much more common in observational studies. And this is sort of that idea of when do you start your follow-up? It's especially important in comparisons of ever or never exposed. I like to ask people, when does never start? Because if you don't know when never starts, then you can't have never as an exposure. You don't have a baseline. Structural positivity violations. So this, and we'll talk a little bit more about it later, but the idea that in an observational study, you may end up including people who are just absolutely incapable of experiencing one or more levels of the exposure. Whereas in a trial, everybody who enters your trial is at least given given assignment with a pre-specified probability that is not 1 or 0. And ill-defined causal questions are certainly more common in observational studies, because in a trial, you at least have to say what you're going to give people, and you at least have the assignment to fall back on. So step 1 is really just sort of say what you're going to do and think about what parts are important. Step 2, choosing the most feasible study design. Here, again, this is probably things that you think about a lot already. Can you conduct a randomized trial? Is it ethical, logistical, or financially possible? Do we have observational data, or can it be collected? But the third piece, where, if you're kind of no on all of these others, the third piece is, are there things that we know that we can use to make some kind of informed best guesses? And this is where we can think about starting to bring in the idea of simulation modeling for causal inference. So if we can't have that perfect ideal trial, then our first preference might be to have a randomized trial if it's feasible. If we can't have a randomized trial, we might like to have an observational study. And there we might prefer a cohort study, but we can also think of our case control study as sampling from that perfect ideal randomized trial. But lots of times there are things we want to know where we don't have enough data. Maybe we want to know if an existing treatment would work well in a new population, how good an existing treatment would have to work for a new indication in order to be useful to try it out, how good a hypothetical treatment would have to be in order to solve a problem that we have. And so here, this is the idea of, well, if we don't have any data, or we don't have much data, or we don't have the right data, but we at least know some things, then maybe we can emulate what would have happened in our perfect ideal randomized trial with a causal simulation model. So the idea here is that all simulation models basically estimate counterfactuals, because you just set up a little universe of your simulation model and then you change some things, and whatever comes out the other end is a counterfactual in the universe of your simulation model. But a causal simulation model is a simulation model that's designed to estimate counterfactual outcomes that would have been observed in our universe if you had run the trial that you wanted to run, if you had done the study that you want to do. And this imposes some specific constraints on our simulation models. Very briefly, I want to just sort of mention how the different types of simulation models kind of fall under this. So we might use a group level model, like a compartmental Markov or SIR model. So that SIR is susceptible infectious recovered, that you may have seen in COVID papers. Or we can have unit level models, like individual level or agent-based models or microsimulations. And these, if we think about them in the target trial framework, they're really the same kind of model, but just with different assumptions made to collapse different pieces of information. And so that leads us into specifying our assumptions. So we have to have assumptions. The very first assumption that we're going to make, assumption 0, is that we can estimate an average causal effect, and that we can do so by comparing estimates of average counterfactual outcomes within a specific group of people. Everything else tells us whether or not we can estimate the counterfactual outcomes that would have been observed for a specific group of people. So you can only get a causal effect if this makes sense. But now the question is, how do we estimate what would have happened to this group if exposure 1 versus what would have happened to the same group if exposure 0? And for that, we need the first set of assumptions is the idea of known measured confounding, which is that all of the variables that cause our exposure and our outcome are known and measured in our data. In an RCT, randomized controlled trial, this is pretty much guaranteed at baseline. But as soon as you move past random assignment, after baseline, all bets are off. Confounding can start creeping in. Related to that, we also need the idea of no open colliders. And I'm going to just sort of high level over what those are, but basically common effects of the treatment and the outcome are known and not conditioned on or in the data or in the analysis. The most common type of this in all studies is loss to follow-up. Loss to follow-up is something we have to condition on because we only have people in our studies who are not lost to follow-up. And it's very possible that loss to follow-up may be a consequence of exposure and either a consequence of the outcome or more likely a consequence of a variable that is also a cause of the outcome. Together, these two sets of assumptions are called exchangeability. And this basically says we know all of the variables and have measured them that are needed to estimate those counterfactuals. The second or third assumption that we need is positivity, which we touched on a little bit, the idea of structural positivity. But basically positivity says everybody that we're studying has a chance of getting every exposure level that we want. In a randomized control trial, we guarantee this by design because we've got an allocation scheme. But it is possible that like nobody could adhere, in which case we wouldn't have positivity for adherence or for the actual exposure that we're trying to give people in a trial. But generally, the easiest way to think about it is we want to include in our studies those people for whom we don't yet know what to do, for whom we're still trying to make a decision. And so if people are always treated or never treated, then they shouldn't be in our study because we don't have any uncertainty about what to do for them. And there isn't any variance in what's happening to them in the world. Then the last assumption, which we've met already, is consistency. And this is the formal way of saying we need to specify our causal question clearly. In the sort of mathematical framing, this means that the exposure that we're measuring is the exposure that we would like to investigate in the counterfactual world. And those assumptions are required for our ideal perfect trial, our actual trial, our observational study. Once we start thinking about causal simulation models, we have to add some additional assumptions. And this is kind of the trade-off where the less data that we actually have, the more assumptions we're going to have to make. But the more assumptions we make, potentially the more broadly we can make our causal inferences. So there's some trade-offs here between these different approaches. Thinking about a group level model, in a group level model, we're basically taking our ideal trial and lumping people together by specific characteristics. And the key assumption here really is that each of these categories that we lump people into has incorporated anything that's relevant for the causal effect. So within the category, we can treat individuals as completely causally identical or homogeneous. And so this is really an effect modification or effect heterogeneity assumption. In individual level models, we're simulating individuals with individual virtual lives. And here we're assuming similarly these additional effect modification or effect heterogeneity assumptions, but we're doing it both explicitly through the choice of covariates that we're simulating and implicitly through the choice of population to model and the source of our covariates. And that's like a whole nother, well, that's like my dissertation. So I'm not going to go too much into it, but if anyone has questions, happy to talk about it. But so those are the types of assumptions we want to make. How do we know what assumptions we're actually making when we specify our study design from our ideal trial? There, really the best way is to think about drawing out everything we know in set of causal relationships. And so there's a link here to an intro to directed acyclic graphs lecture I have on YouTube, which goes more into how do you draw a graph, how do you read a graph, and what does it tell you about what you should be choosing for your adjustment set. So once you've done that, you have a good question, you have a perfect trial you'd like to do, you have a study you're going to do, and you know what assumptions you're making. The last step is to actually analyze your data, taking everything that you've figured out till now. And so if your exposure is simple, you can do almost any analysis you want, and you will be able to get the causal effect, so long as you include in that analysis those assumptions, i.e. those variables that are required to identify your causal effect, and you've got a good causal question, etc. But as soon as you start moving into complex exposures, you really need methods that are going to be flexible to deal with those complex exposures. And so here, the most comprehensive set of methods is called the G methods. And the G methods, you can think of the G as standing for generalized. Not really clear to me if it actually does stand for generalized, but it acronyms into generalized. So G methods, generalized estimation of our causal effects to these complex exposure scenarios, and particularly to ones that have this treatment confounder feedback. And that's important because the treatment confounder feedback is where all the other methods really fall apart. So very briefly, there are 4 types of methods that fall under the umbrella of G methods: inverse probability weighting of marginal structural models, parametric G formula or other ways of estimating the G formula, doubly robust estimation, which you can do in a number of ways, but if you use machine learning, then TMLE is a good example of that, and then G estimation of structural nested models. And to think about very, very roughly what those are, you would want to use these G methods in scenarios where you might normally have thought to use these other methods. And in fact, inverse probability weighting uses the propensity score as part of the weights, or 1 minus the propensity score, but is based on the propensity score. So if you would have normally used a propensity score in a simple exposure setting, you could think about using inverse probability weighting. If you normally would have used standardization or just a regression, which is basically a standardization approach, then the G formula might be the appropriate approach. If you would have used instrumentals, you can show that instrumental variables are a special case of G estimation. So if you would have used an instrumental variable, you might want to use G estimation. And then doubly robust basically just brings the best of both worlds from IPW and the G formula together. So you could use it in any scenario where you would use either one of those. So why do we need the G methods other than just giving students something to fret about? So both the G methods and standard approaches will control for confounding. So if we have, confounding that happens at baseline or confounding that happens after baseline, all of our methods are going to control for confounding. But when we use traditional methods, the way in which they control for confounding after baseline can create additional bias. So it controls for the confounding bias, but it introduces collider bias. And as I mentioned briefly in the assumptions, we need to assume that we don't have any open colliders. Standard methods open up colliders that were not otherwise open. The G methods are specifically designed to not induce this additional bias during the analysis phase. So the G methods is a whole suite of tools, as I said, but it all in the end boils down to the only formula is the G formula, which is this cross stitch behind me. So if you only have one, that's a good one time to learn one, that's a good one to focus on. So I know we're getting close to the end of our time. So I think I'm just going to kind of go very high level through these last few slides that talk a little bit about the G formula. But the first point is that IPW and the G formula are two sides of the same coin. they estimate the counterfactual outcomes from the joint probability distribution of your exposure, your outcomes, and all the variables that you need to identify your causal effect. But the G formula focuses on estimating the conditional distribution of the outcome given the covariates and the conditional distribution of the covariates. The IPW focuses on estimating the conditional distribution of the exposure given the covariates. And so one way to decide between these is which of those pieces of information do you think you can estimate better. But otherwise, they're really trying to do the same thing. And so this is one reason why just focusing on the G formula is useful, because the G formula is pretty easy to think about relatively. Because it's just about joint probability distributions and conditional probabilities. So what does that look like? It's a generalization of standardization to both time varying and time invariant settings. The formula part is just an equation that relates the observational data to the counterfactual data. So in the simplest case, this is what the G formula is. It says that the counterfactual outcome is equal to the joint outcome distribution when we set, or can be obtained from the joint outcome distribution when we set the exposure to the intervention level, and that can be calculated by just summing over the history of the variables, where we don't need the distribution of the exposure because we're fixing the exposure, but we do need anything that includes the exposure in the conditional. We do need exposure there. So here L is the sufficient set of confounders that let us identify the causal effect. So when we have a simple one-time point exposure, this is the G formula, and we can hand calculate it if we want. So we have the conditional probability of the outcome in each strata of covariance and exposure, and then the probability of being in each covariance strata. When we start having complex exposures and complex time points, it gets a lot more messy, and we often don't really want to write it out, but we still have the same basic components. So we have the conditional probability of the outcome in this within strata of the history of all the variables that are relevant, and we have the distribution of all of those strata. And so it's really is just that summation of conditional probabilities makes up the G formula for whatever scenario we want to do. And so if we have a very small number of categorical covariates, we can just solve that by hand. Usually we have too many, and so we use Monte Carlo simulation, but we can also use other approaches. And Monte Carlo simulation is where we now link back to the idea of causal simulation models. Because when we simulate individual level simulation models, we simulate individual life histories based on conditional distributions of all the relevant variables. And we do this using Monte Carlo simulation. So causal simulation models aren't the G formula, but we can use them to estimate the G formula if we've specified them correctly. And the main difference is that instead of estimating all our conditional distributions from a single data set, we have to make assumptions about them from wherever we can get them. And that's where those additional effect modification assumptions come in. So with that, a couple summary points. So if we want to use data to inform our decisions, then we're trying to estimate causal effects, and we need to think about our causal inference assumptions. The first big hurdle is specifying a good and clear causal question. We can use what we know about how RCTs work in a theoretically perfect world to design a good analysis and a good study. And then once we do that, we can just think about everything boiling down to the causal effects coming from the joint distribution of the exposures we're interested in, the outcome or outcomes we're interested in, and then all of our assumptions about the causal structure of the world. So with that, I will stop and leave time 10 minutes or so for questions. I can stick around for a couple more minutes if there's more questions than that.
Fantastic. Thank you very much, Ellie. That was an absolute tour de force. That was marvelous. If everybody could mash your reactions pad to show some appreciation for Ellie. Thank you very much for that. I'm going to give you a little bit of time to pop any questions that you have into the chat. And I can give some, I'm going to pull up the chat window. If anybody does have any questions, then now is your chance. And while you're doing that, I'm going to this guy. Oh, while I'm doing that, I'm going to stop recording. And that's what I'm going to do. Stop recording.